you've got your proportion or your percentage and you want to measure how accurate it is, and we can calculate a standard error in fact a similar way to how we did it for continuous data, except now we take into account the standard deviation, which isn't really very interesting, how much an individual differs from the proportion, because the individual's always going to be kind of yes or no, 0 or 1, but that standard deviation is the proportion multiplied by 1 minus the proportion. So if you calculate that, divide it by the number of observations, take the square root, that gives you the standard error for the proportion. And if we do that for the proportion of diseased calves, we had 0.08 calves were diseased, so we multiply it by 1 minus 0.08, 0.92, divide by 188, which was our sample size, total number of calves, and take the square root, we end up with a standard error of 0.02. So that tells us that if we were to do another study, then we would end up with the proportion of calves with disease would be expected to differ from this 0.08 by 0.02. So it gives us a feel for how accurate that 0.08 is. So not particularly accurate, really. It's expected that if you took a new sample, then it's expected that you'd have sort of either 0.1 or 0.6. So you can't sort of say it's exactly 0.08. Of course, you could summarise that as a percentage alternatively, and the formulae then, instead of 1, you just put in 100%, and it comes out, it's going to be, the standard error will be simply multiplied by 100, so you just get 2%, so you'd be able to say, yeah, 2% of the calves have got the disease. So that's fairly straightforward, I think, getting the proportions or percentages and a measure of their accuracy. Key thing is putting in this proportion into 1 minus it. And just as we had for continuous data, we can also give a confidence interval to our proportion, and it's calculated in exactly the same way. And so instead of the mean, we have the proportion, and we just say plus or minus 1.96 multiplied by the standard error. So that was the same formulae as we had for continuous data. And if we put our proportion of 0.08 and the standard error of 0.02 into that formulae, we get a confidence interval of 0.04 up to 0.12, or put maybe a bit more, in a way more easy to understand, from 4% to 12%. So that's the 95% confidence interval for our proportion of diseased calves. So we can be, if we did another study, we'd be 95% sure that the mean would lie between, the number of diseased calves would be between 4 and 12%. So quite a large difference. Yeah, I've added a note here which is relevant for all types of data. We're using 95% confidence intervals. Occasionally you'll see people using other types, but it's very uncommon. So for example, you could say I want a 90% confidence interval. That would be a bit narrower, and that would be the range within which you'd expect a statistic to lie 90% of the time. Or you might want a range where you might want to be able to be 99% sure that your value is going to be in a particular range. So you can get a 99% confidence interval. And they would be achieved by substituting the appropriate number for the 1.96, because if you remember that related to that normal distribution, these tails either side. So for 99%, you would move these a bit to the side to the point where 99% of the means would lie within that region. But more often than not, I think the convention is to use 95% confidence intervals, and this helps tie in with statistical testing as well, so there's that advantage. Another thing to note is the formulae we've used, this formulae for the 95% confidence interval for the proportion, assumes the distribution is symmetrical. But for proportions, they're generally not completely symmetrical unless you've got a very large sample size. So for example, this is a sample size of 15. That's not completely symmetrical. It's not bad, but it's not symmetrical. And so if you want to get a more accurate confidence interval, you can use something called the binomial distribution, and it takes into account the skewness of the distribution. If you did this for our sample, you would get a slightly non-symmetrical confidence interval, so it's 5% to 13% compared to the symmetrical 4% to 12%. So here the 5% is only 3% below our 8%, which was the overall proportion of calves with the disease, and it's got a higher upper limit. So that is actually a better confidence interval, but you do need a package to calculate it or to use distribution tables. So in practice, people unfortunately don't bother to do that usually, even with small samples, and they'll use this more conventional formulae. But I thought it was worth mentioning, because if you have got the patients to obtain a better confidence interval and you can find a package that would do it for you, those would be more appropriate for proportions.